Hi, so we're ready to start in chapter 9. So this will be new material after midterm 2. This will be on starting in chapter 9 will be content covered in midterm 3. So chapter 9 is titled Radicals and Complex Numbers. In section 9.1, the first thing we want to look at is the definition of an nth root, right? So the very first concept in section 9.1 is kind of setting a tone for what a square root is, just to understand that, and then we could start talking about other types of roots that aren't necessarily a square root, but what we can call an nth root. So like maybe a third root or a fourth root, etc. So the definition of a square root is the following. So b is a square root of a if b squared equals a. Right? So in example 1, we are identifying some of these square roots, right? So we want to think of, like, for part A, think of some numbers that if I square them, it will equal 64, right? So it turns out that negative 8 squared equals 64, and positive 8 squared equals 64. Right, so the square roots of 64 would be negative 8 and 8, right? So in other words, we're thinking about b squared being equal to 64 and solving for b, essentially, right? So if I take the square root of both sides, we get b equals plus or minus the square root of 64, which gives me b equals plus or minus 8, right? So that's kind of the line of thinking here with these problems, right? So then for 16, right, negative 4 squared equals 16, but also positive 4 squared equals 16, right? So when I square a number, if it's positive or negative, I'm going to get a positive back, right? So the square roots of 16 would be minus 4 and 4. So for part C, we're trying to find the square roots of 1. Well, negative 1 squared equals 1. And positive 1 squared equals 1. So the square roots would be negative 1 and 1. Right? And then lastly, we have negative 100, right? So again, kind of what we're thinking along the lines is b squared equals negative 100, and we want to try to solve for b, right? That's kind of what we're looking for. So if you think about this for a moment, if I take any number squared, this will always be positive, right? Because, if I take a negative number squared, that's going to be positive. If I take a positive number squared, it's going to be positive. So whenever I'm squaring something, what it equals should always be positive, right? So in other words, there are no real values squared that equal a negative value, right? So if I square any real number, I'm not going to get a negative number back, right? Now, it's possible to solve like b squared equals negative 100 if we have, maybe some complex numbers, but we haven't introduced those yet. So that's the part here, is if we consider we're only stuck in real numbers, right? So then example 2, we want to simplify these square roots, right? So these square roots, it's always understood that's like it's a positive square root, right? There's a positive in front. So like if we look up here, notice this part I'm circling in blue. I wrote b equals plus minus square root of 64, right? So for these, notice there's no minus or plus in front, so it's understood that these are positive square roots, right? So the square root of 81, right? The square root of 81 is just 9, right? The square root of 36 over 49 is equal to radical 36 over radical 49. right? So whenever you have a fraction, like if I have the square root of a over b, you can actually split this up to be the square root of the numerator divided by the square root of the denominator, right? So this is a property of square roots, right? So when you have the square root of a fraction, I think this is probably the easiest way to think about it, is the square root of the top and the bottom. So the square root of 36 is 6. The square root of 49 is 7, right? So that gives me 6/7. And then for part C, we have radical 0.09, right? Now for me, I think the easiest way to think about this one is to actually write this as a fraction, right? So this would be 9 over 100, right? Because that's 9/100, 0.09. So using this property of radicals, we can rewrite this as the square root of 9 over the square root of 100, right? So this just becomes 3 over 10, right? 3/10, which, since I converted my decimal to a fraction, maybe I want to put my answer back in a decimal, right? So 3/10 would be 0.3, right? So in other words, again, just to kind of check this, the square root of 0.09 equals 0.3. So that implies, right, that 0.3 quantity squared is equal to 0.09, which it is, right? So those go hand in hand, right? We're trying to find what number squared gives me the answer underneath the square root, the radicals. Right. So on the next page, so we've talked about perfect squares before when we were factoring. So we can just give a definition of perfect squares, right? So a perfect square is the product of a rational number multiplied by itself. All right, so some examples are actually the numbers that we saw in the previous example in parts A and B and C. So by this definition, 81 would be a perfect square. 36 over 49 is a perfect square, and also 0.09, 9/100. Right? So remember, a rational number, right? That's a number that you can write as a fraction, right? And this is just a reminder that I gave you a list of perfect squares and perfect cubes earlier when we were doing factoring. So that's on Canvas if you want to refer to that, right? So I gave you a list of perfect squares. If you took like an integer squared, so I think I started at 1 and went through like maybe 15 or something, right? So you can refer to that list as well. So then, for example 3, we want to be able to kind of estimate these square roots in between two different consecutive integers without using our calculator, right? So kind of the way I like to think about this is if we think about that list of perfect squares that I gave you, right? So that was, like 1 squared equals 1, 2 squared equals 4, 3 squared equals 9, 4 squared equals 16, 5 squared equals 25, 6 squared equals 36, 7 squared equals 49, and so forth, right? So if we look at that list, we want to kind of think about what two perfect squares is number 13 in between, right? So 13 is going to be here, right? Make that a little less bold, right? So in other words, 13 is in between the numbers 9 and 16, right? So that turns out if I take the square root of all the numbers, my inequality still holds. Right, so I'm just taking the square root of 9, 13, and 16, right? My inequality would still hold. Then I could evaluate the square root of 9, right, is 3. and I'll just leave square root of 13 like this, and then the square root of 16 is 4, right? So what that tells me is the square root of 13 is in between 3 and 4, which makes sense, right? It's going to be somewhere in between these two values, right? And then for 42, right, 42 is going to be in between here, right? So 42 is in between the perfect squares 36 and 49. So then I can take the square root of everything, right? So the square root of 36 less than the square root of 42 less than the square root of 49. And then simplify, so radical 36 is 6 and radical 49 is 7, right? So that just tells me that radical 42 is going to be somewhere in between 6 and 7, right? So this kind of way to kind of just estimate, you can kind of do mentally, just to kind of get a ballpark figure for what the radical should be around, right? So then example 4, we're going to use our calculator to approximate the following square roots, right? So I want to take radical 13 and approximate this, maybe, I don't know, like 4 or 5 decimals or something, right? Using your calculator. So let me pull up a calculator. All right, so the first one we want to do is radical 13. So we do second square root, right? So you want this one, the square root of 13. I can hit equals, right? And then the other one is the square root of 42. Right, so we get those values, so we can estimate those, right? So I can write those down in my notes. So radical 13 is going to be approximately 3.60555, right? If we want maybe 5 decimal spots. And then radical 42 is approximately 6.4807, right? So we can use our calculator to get those approximations, right? But it's important to understand that radical 13, that's an exact value, right? But this value over here, this is an approximate value, right? So there's no way for me to write radical 13 exactly besides the symbol radical 13, right? And actually, that's a type of an irrational number, right? An irrational number is a number that you can't write as a fraction, right? So for example, the number pi, right? Or Euler's number e, right? Those are both rational numbers. So if I take the square root of a non-perfect square, that's also going to be irrational, right? So I can't possibly write out all of its decimal parts, right? So the only way to make it exact is to keep it with its square root symbol, but we can approximate it and get some values that way, right? So then example 5, we want to simplify the square roots if possible, and notice for A, B, and C, and D, we have some negatives. We have negatives under the radical and some in front, right? So maybe we can kind of investigate how that would work. So anytime you have the square root of a negative number, that's going to be, not a real number, right? Or in other words, it's undefined, right? So like the square root of negative 81, this would be, not a real number, right? So we actually get a different kind of number from that we'll, maybe investigate, but it's later on, but not in this section, right? Part B, if the negative's out in front, that's okay, right? Because negative radical 64 is equal to negative 1 times radical 64, right? So we're taking the opposite. In other words, what's the opposite of radical 64? So radical 64, right? I can simplify that. This part, that's 8, right? So this just becomes negative 1 times 8, which is negative 8. Right, so we can get that okay. So part C, similarly, that's going to be okay to evaluate, right? Because that's equal to negative 1 times radical 0.25, right? And again, if you can't think about the answer maybe in decimal form, a technique is we can change it to fraction, right? So this would be the same thing as -1 times the square root of 25 over 100, right? So 0.25 is 2500, so 25 over 100. So this would be equal to -1 times, and then applying that rule I showed you, is you can take the square root of the numerator divided by the square root of the denominator, right? We can just rewrite that square root of a fraction in that fashion. So that becomes -1 times 5/10, right? Which is equal to -1 times 1/2, which is -1/2, right? And if you want that answer in decimal form, that would be equal to -0.5, right? And then the next one, remember, I can't have a negative value underneath the square root, right? So this would be not a real number, right? In other words, this is undefined, right, for real numbers, right? So if we're stuck in the real number system, we can't take the square of a negative number. Right. So now ready for concept 2. So we're looking at the definition of an nth root, right? So let's maybe try to explore some other types of roots other than square roots. So the definition is the following. So b is the nth root of a if b to the n equals a, right? So this is more general than the square root. We can have different kinds of roots. So example 2 is a square root of 4 because 2 squared equals 4, right? Another example, 2 is a third root of 8 because 2 cubed equals 8, right? And another example is 2 is a fourth root of 16 because 2 to the fourth equals 16, right? And so forth, right? So that's just applying this definition at the top, right? Just putting different values in for n and a and b, right? So just for some common terminology, right? If I have the nth root of a, right? This n value, that's known as the index, and the a, that is known as the radicand. Right, so that's the value underneath the square root is called the radicand. And then this symbol, that's called a radical sign. And then if you have like the third root of a, that's also known as the cubic root. Right, so anytime you have a third root, we can call that the cubic root, just like the second root is called the square root. So just like I mentioned that, if you have a square root of a, also another thing with the square root, if you have an index of 2, is you typically don't write that, right? So if you have a index of 2 of a, right, square root of a essentially, you don't have to write the index, so that's just known as a square root, right? So just a note, so you don't typically write an index of 2. right? So then I have some facts here to write. So the first one is if n is greater than 1, is an even integer, and if a is greater than 0, then the nth root of a is the principal, in other words, the positive nth root of a. Right? So an example of this would be the square root of 9, or the principal root of 9, is 3. Right? The positive root of 9 is 3. Another fact is if n is greater than 1, is an odd integer, then the nth root of a is the nth root of a. Right? So example would be if I have the third root of 8, we get 2. Also, the cubic root of negative 8 is negative 2. Right? So something that we want to pay attention to is if I have an odd root, I can take if my index is odd, right, I can take an odd root of a negative value, right? And that just comes to how negative numbers work, right? So if I come over here real quick, if I take for example, let's say negative 2 to the first power, I get negative 2, right? If I take negative 2 squared, that's negative 2 times negative 2, which gives me 4, right? And if I take negative 2 cubed, that gives me negative 2 times negative 2 times negative 2, which this is going to be negative, right? Because these two symbols, these two signs of the first two, that makes that positive, right? But then I'm multiplying a positive times this negative, which gives me a negative value, right? So this would be negative 8. And then negative 2 to the fourth would be negative 2 times negative 2 times negative 2 times negative 2, which that's going to give me positive 16, right? So notice when you have an even exponent, you're going to have, it's going to force you to have a pair, right? Because it's a multiple of 2, a pair of negative signs. So if you're multiplying an even number of negative signs, it's going to be a positive number, where if you have an odd number, you're always going to have one negative sign left alone that doesn't have a partner. That's going to make the whole product negative, right? So following along that idea, that's why we can have we can take an odd root of a negative value, right? So that's what that is speaking to a little bit. And then the third point that I want to write is if n is greater than 1, is an integer, then the nth root of 0 is 0, right? And that doesn't matter if n is positive or it doesn't matter if n is even or odd, right? Just if n is greater than 1 and it's an integer, then if you take the nth root of 0, you get 0 back, right? And then here's just a table of some perfect cubes and some perfect fourth powers and some perfect fifth powers and so forth, right? And don't forget, I also gave you a list of perfect cubes earlier in the course, right? So we're just squaring or cubing integers, right? So these were like the first 5 on that list, and I think I maybe went through 10 or something like that, right? Maybe 15. Right. So on the next page, page 4, we just want to find or simplify if possible, right? So if I take the fourth root of 16, right, that's just going to be 16, right? And that's because 2 to the fourth equals 16, right? So you're kind of like working backwards. You're trying to think of, the fourth root of 16 is equal to 2, right? Sorry, I'm thinking a little ahead of myself. And that's because 2 to the fourth is equal to 16. right? So when you look at that, you're trying to think about, what number, if I take to the fourth, gives me positive 16, right? So then the third root of 1,000, right? That's going to equal 10, right? So in other words, 10 cubed equals 1,000, right? And again, something we want to note the difference of is if I had something like x to the fourth equals 16, then if I take the fourth root of both sides, then this would, on this left side, that would leave me with just x. This would be equal to positive negative the fourth root of 16, which this would be equal to x equals plus or minus 2, right? So in this case, we get plus or minus 2, right? Because if I take negative 2 to the fourth, I also get 16. So this is solving an equation, right? I'm trying to find all values of x that make this true. But this is different, right? Again, this is finding the positive root of that. You're just evaluating that root. So your answer is not going to be a positive or negative here, right? So remember, anytime you're solving an equation and you want to take an even root of both sides, you have to introduce this plus or minus sign on one of the sides, right? So like here for part B, I don't have to worry about that because this index is 3. It's not even, it's odd, right? So the third root of 1,000 is just 10, right? So then part C, we want to take the fifth root of negative 1. And this is possible, right, because my index is not even. As long as that number, that index is odd, you can take it of a negative number, right? So this is just going to equal negative 1, right? Because negative 1 to the fifth power is equal to negative 1, right? And then for part D, right, we're thinking about what value to the fifth power is equal to 32, right? Well, that's 2, right? So 2 to the fifth equals 32. And then part E, if we think about what's the fifth root of 100,000, right? So, it turns out like if I take 10 to the, like 20th power, this would be 1 with 20 zeros. 20 zeros behind it, right? So if we count the number of zeros, that's going to tell you the exponent of 10, right? So this would just be equal to, there's 5 zeros, so this would just be equal to 10, right? Because 10 to the fifth power gives you 100,000. So the answer would be 10, right? So 10 to the fifth equals 100,000 is what we were trying to think about. Right? So then part F, we have the square root of negative 36. So notice that there's no index written here, so it's understood it's a 2, right? It's a square root. So that's even number. So this would, not be a real number. Right? In that sense, negative 36 is less than 0, right? We can't take the square root of a negative value, right, if you're stuck in the real number system. So then part G, we have the cubic root of negative 27, and that's okay, right, because that index is odd. The index is 3. So we're thinking about what number cubed gives me negative 27. Well, negative 3 cubed would be negative 3 times negative 3 times negative 3, which is in fact negative 27. Right? So the cubed root of negative 27 is equal to negative 3. Right? So that's my answer, negative 3. Right? All right, so then concept 3, we're looking at roots of variable expressions. Right? So I kind of introduced this a little bit already, like up here, where I took the fourth root of x to the fourth. So notice how this just becomes x, right? So these are inverses of each other. Raising something to the fourth power and taking the fourth root of it, those undo each other, right? It's kind of like addition and subtraction, right? They're inverse operations, and like multiplication, division, right? So the first bullet point I want to make here is if n is a positive odd integer, then the nth root of a to the n is just equal to a. And the second thing I want to say is if n is a positive even integer, then a to the n, the nth root of a to the n is equal to the absolute value of a, right? So this, these absolute value bars are needed, right? The absolute value bars are needed since a is greater than 0, or a could be less than 0, right? But the principal roots are positive, right? So this a value could be, positive or negative under there, but we're doing a principal root. So remember, the principal roots are positive, right? So that's, by that notation, that's a principal root, right? So that's why we need to take the absolute value just to force that to be positive. So in part A, for example 7, we're just applying those rules. We want to simplify these expressions. So the square root of -4 quantity squared, right? That's gonna, since that's an even root, that's going to be equal to the square root of -4, right? Just by following number 2, right? So since those ends match, right, those are just going to go away, and we get excuse me, the square root of -4, which is +4, right? So then the cubic root of -4 cubed is going to be equal to, so that we don't need the absolute value bar since this is an odd root, so this would just be equal to -4, right? So then part C, notice we have an even root again, right? A root of 2. So this would be equal to the absolute value of y plus 9, right? Part D, we have an odd root, so this would just be equal to t plus 1. And then for part E, you could rewrite this a little bit. This would be the 4th root of v squared to the 4th, right? So I just rewrote that a little bit so that way the index and the exponent match, right? So this is, since this is an even root, this is going to be the square root of v squared, right? Or excuse me, I meant to say the absolute value of v squared. But notice that, if v, no matter what v is always going to, v squared is always going to be greater than or equal to 0. Right, so if I take a negative number squared, I get a positive number. If I take a positive number squared, that's positive. And if I take 0 squared, I get 0, right? So v squared is always going to be greater than or equal to 0. So it turns out that I don't actually need those absolute value bars. So that's just going to be equal to v squared, right? Because that's always going to be positive inside, right? So just a note, so if the nth root of a to the n equals the absolute value of a, and a is greater than or equal to 0, in other words, non-negative, then we can drop the absolute value bars. And that's like in part E, right? So just like right here that we did. Right, so we just need to guarantee that that's greater than, going to be greater than or equal to 0. Right? So on the next page, page 6, we want to simplify the expressions, and we're assuming that all variables represent positive real numbers, right? So we're kind of applying that general statement I just made at the bottom of the previous page. So in other words, my variables are t, y, x, a, and b. So we're saying that t is greater than 0, y is greater than 0, x is greater than 0, a is greater than 0, and b is greater than 0. Right? All variables present below are positive, right? And those are, I believe, the only variables. Right? So, so the square root of t to the 6th is equal to the square root of, and I can put a 2 here if it helps you remember. That would be t cubed quantity squared. Right? So that gives me, following before, that would be the absolute value of t cubed. But since we know that t is greater than 0, this is just going to be equal to t cubed. Right? I can drop the absolute value bar because t is greater than 0. Right? Therefore, t cubed is going to be greater than 0. Right? So for part B, we have the cubic root of 64y to the 12th. Right? So the cubic root of 64y to the 12th. Right? So I showed you one previous rule with fractions. I can also show you something with a product, right? So in other words, if you have the square root of a times b, that's the same thing as radical a times radical b, right? So you can split up products with the, with the same index, right? And this works really with any root. So I could put the nth root here and make it more general. Right? So in other words, I can rewrite this as the cubic root of 64 times the cubic root of y to the 12th. Right? So we're trying to think about, what number cubed gives me 64. Well, that's 4. Right? And then if I just write this, I'm just going to write the cubic root of y, and then instead of writing 12, I'm going to write 4 to the 3rd power, right? So y to the 4th to the 3rd power is just y to the 12th, right? Because remember, when you have power to a power, you multiply exponents. But this just makes it a little more obvious, right, that when I evaluate this cubic root, this cube, the cube and the cubic root are going to cancel each other out. So this just becomes 4 times y to the 4th. Right? So then this next one, we have the 4th root of x to the 4th over y to the 4th. So this would be equal to the square root of the 4th root of x to the 4th over the 4th root of y to the 4th, right? Which this is just equal to this, the absolute value of x over y, right? Because those to the 4th powers are going to cancel out, right? They undo each other. But this would just equal x over y, right? And that's because, x is bigger than 0 and y is bigger than 0. So those are always positive. So you get just equals x over y. Right? So then part D, we have negative the 5th root of 32a to the 5th divided by b to the 10th. So this would be the same thing as negative 1 times the 5th root of 32a to the 5th over b to the 10th, right? Which this would equal negative 1, so I can split that up as, taking the 5th root of the numerator over the fifth root of the denominator. And then what I can do to evaluate that is in the top, I can split that up because that's a product, right? So that would be like the fifth root of 32 times the fifth root of a to the fifth all over. And then instead of writing b to the 10th, I could write b squared to the fifth and the fifth root of all of that, right? Just to make it a little more obvious. And I forgot my negative times -1 out in front, right? So then this would be equal to -1 times, and then the top part, the fifth root of 32 is 2, right? And then the fifth root of a to the fifth is just a, and then the fifth root of b squared to the fifth is just going to be b squared, right? So this ends up becoming -2a divided by b squared, right? So the next concept that we want to look at is the Pythagorean theorem, right? So just kind of a refresher, you might remember the Pythagorean theorem, but if we have a right triangle, the Pythagorean theorem says, and remember in a right triangle, the parts, the sides of the triangle that touch the 90-degree angle, those are called the legs. And then the longest side, the side that's across from the 90-degree angle, that's called the hypotenuse. Right? So Pythagorean theorem makes a connection between sides of a right triangle, right? So in other words, if I take a leg and square it and add it to the other leg and square it, that's going to give me, that's going to be equal to the hypotenuse squared, right? Or you may have seen it like this before, or if I have a right triangle and I name the legs A and B, and let's say the hypotenuse length is C, right? Then that would give me that A squared plus B squared equals C squared. Right? So that's the Pythagorean theorem. So I have some examples around the Pythagorean theorem. So example 10 is we want to use the Pythagorean theorem in the definition of the principal square root to find the length of the unknown side of the right triangle, right? So I'm trying to find this value. Maybe it's equal to x, right? We want to know what that equals. So x is one of the legs, right? So using Pythagorean theorem, I could have 12 quantity squared plus x squared equals 15 squared, right? So 12 squared is 144, and 15 squared is 225, right? So I can subtract 144 from both sides, and we get x squared equals 81, right? So if I take the square root of both sides, I get x equals plus minus 9, right? But here, we're, Pythagorean theorem, we have length of a triangle. So it's understood that x is going to be bigger than 0, right? So in other words, when we put this in context, x is just going to be equal to 9 centimeters, right? And just I wanted to make one point before that I forgot to write down. I just want you to make note that for the Pythagorean theorem, that this this only works for right triangles, right? So only works for right triangles. Right, so it doesn't work with any triangle. It has to be a right triangle. A right triangle has a 90-degree angle, right? So it has to have a right angle. Right? So then another example applying the Pythagorean theorem is this example 11. So we're told that two cars leave from the same place at the same time. One travels west at 40 miles per hour, and the other travels north at 30 miles per hour. How far apart are they after 2 hours, right? So just maybe some things we need to know is if we just, have a, just draw my compass, right? We have north, south, west, and east. That's what those directions are, right? Another thing that we need to make note of is that distance equals rate times time, right? We're going to need to know this equation, and we've used it before, and it's pretty common classic equation to use in math. So maybe if we just draw a picture, if this is a spot that they leave from, right, then car 1 is driving west at 40 miles per hour, right? So then car 2 is driving at 30 miles per hour, right? So there's car 2 and car 1. What we want to know is, after 2 hours, what's the distance between them? Right? That's what we're trying to find. So if car 2 is going 30 miles per hour, right, the distance for car 2 is going to be equal to the rate of car 2 times the time of car 2, right? So this would just be equal to 30 miles per hour times 2 hours, which equals 60 miles, right? The distance of car 1 would be equal to the rate of car 1 times the time of car 2, which both cars are going, 2 hours. So that would be equal to 40 miles per hour times 2 hours, which equals 80 miles. Right? So if I draw a new right triangle, right, then car 2 is going 60 miles, right? So that would be 60 miles. And then car 1 would be going 80 miles. So the distance between the two cars, right, because the car is going to, be at this point and this point after 2 hours, the distance between them would be this line, right, the hypotenuse. So that's like x, right? That's the distance between. That's what we want to find. So x, is going to be equal to, x squared is going to be equal to 60 squared plus 80 squared, right? That's just following the Pythagorean theorem. So that would give me x squared equals, so 60 squared is 3,600. 80 squared is 6,400, right? So if I add those two together, that gives me 10,000, right? So then if I take the square root of both sides, I would get x equals plus minus. So the square root of 10,000 is 100. So that would be, and again here using Pythagorean theorem, it's understood that this distance is positive, right? Distances are positive. So this x value is equal to 100 miles, right? So the cars are 100 miles apart, right? So one thing you want to notice in both these examples, notice my value for all sides of the right triangle were integers, right? They were whole numbers, right? So when that happens, we call that what we call a Pythagorean triple, right? So another common one is 3, 4, and 5, right? So that's not always going to happen. That's a special case, right? So again, we call that Pythagorean triples when each of the sides are a whole number, right? So there's no decimal or fractional part, right? Right. So then concept 5, we look at radical functions, right? And this is the last concept in this section. So I have some notes for this. So let's define what a radical function is and some things about it. So if n is an integer greater than 1, then a function written in the form f of x equals the nth root of x is called a radical function. Right, so if I can write a function in that form where n is an integer greater than 1, then we call that a radical function, right? So then some notes here is if n is even, then the domain of f is the interval from 0 to infinity, including 0. If n is odd, then the domain of f is all real numbers, so negative infinity to infinity, right? So we want to pay attention to those domains, right? And that's actually what we're going to do for the next couple of things, right? So for part A, we have f of x equals the square root of x plus 5, and we're trying to find what's the domain in interval notation. Right, but something you want to notice is in this form, the only thing underneath the radical, the only thing in the the part that's the radicand, right? The only thing there is the x value, where in this case it's x plus 5, right? So what you're going to do if you have an even root is you're just going to take whatever's underneath the just take the radicand, the part underneath the radical sign, and just make that greater than or equal to 0, right? Because we need that value to be greater than or equal to 0, right? So then if I solve for x, so I would subtract 5 from both sides, we get x is greater than or equal to negative 5, right? So that's my domain of f, right? And we're asked to write this in interval notation, so this would be negative 5, right, including negative 5 all the way to infinity, right? So that's the domain of f, right? So then part B, we have the cubic root of t minus 9, right? So since this is an odd root, the domain is just going to be all real numbers, right? And then for h, so this is an even root, right? This is like a 2 here. So remember, we just don't write that. So this, what we care about is we want the radicand to be greater than or equal to 0, right? So I need to solve for a. So I can subtract 1 from both sides, and we get negative 2a greater than or equal to negative 1, right? And then I can divide both sides by negative 2. So since I'm dividing by a negative number, remember I got to flip that inequality. So that would be a less than or equal to 1/2. So then that's my domain. So my domain, it would be negative infinity to 1/2, including 1/2, right? That's the domain of h, right? Because it's a less than or equal to 1/2. So that's what that would be in interval notation, right? So then lastly, the last example that I want to go through is we're given a function, and we want to find the domain of f in interval notation and also graph that function, right? So this is a radical function, right? So since that's a square root, right, again, we just want to take the radicand and set that greater than or equal to 0, solve for the variable, solve for x. So that would be x greater than or equal to negative 4, right? So the domain of f would be negative 4 to infinity, right? So then if we want to make, if we want to graph this, right, by making a table of ordered pairs, right, we can just come over here and make a table. Right, so we can plug in negative 4, negative 3, 0, and 5, right? These are the values I picked. And the reason why I picked these specific values, if I plug them in, it will give me whole numbers for the y coordinates, right? So if I plug negative 4 in, I'll get an output of, so this would be, so f of negative 4 would be equal to the square root of negative 4 plus 4, which equals a square root of 0, which equals 0, right? So I get 0 for that coordinate. So then f of negative 3 would be equal to the square root of negative 3 plus 4, which equals a square root of 1, which is 1, right? And if I put 0 in, f of 0 is equal to the square root of 0 plus 4, which equals the square root of 4, which equals 2. And then f of 5 is equal to the square root of 5 plus 4, which equals the square root of 9, which is 3. Right, so we're able to get these values. So then let me actually get some graph paper. Right, so we can graph this function. Right, so there's my x-axis, my y-axis. So 1, 2, 3, 4, that's -4, so forth. So I just want to plot these points, and I can start to see what the graph looks like. Right, so the first point was -4, 0. So that's going to be here. My next point was -3, 1, right? So it's here. And then we have 0, 2, which is here. And then the next point was 5, 3, which is here, right? So what we're going to get is kind of like almost like a half a parabola, half a U shape. It's going to look like this roughly. Right? So there's the graph, right? That's what we're asked to do. So if you wanted to see this, on your graphing calculator, right, you could just plug this into y equals. So I can plug this in y1. So we have the square root of x plus 4, right? So then if I graph this, we can see what the graph looks like, and you can kind of see that half a U shape like we had, and then I can go to second table, right, and then I can get some a table of values. So some of the values we had, right, and notice if I pick a value less than -4, we get this error message, right, because we're taking the square root of a negative number at that point. So the domain for this was -4 to infinity. So you can see that's the first value where I get a real number solution, and then you can see the other table values, right, that we had seen. Another thing I just want to point out really quick in your calculator that you'll need from this section is notice, if you want the square root, you hit second and then this x squared button. There's a square root above that. If you want other roots, you'll hit the math button, and then you'll notice like this 4 is a cubic root, and then if you want something else that's not a cubic root, like maybe a fourth or fifth root, you'll hit option 5, right? So let's say you want to find I don't know, maybe the fifth root of 172, right? Maybe you want to approximate this in your calculator, right? So what you would do, let me open the calculator back up. You would just hit 5, and then you would hit math, and then you go down and pick the one with the x in it. And notice that 5 went where the x is, and then I think it was 172 what I written, and then we hit enter, and there's the decimal approximation, right? So that's the fifth root of 172. So that's how you can grab those other roots, right? All right, so that's all I have for this section. Let me know if you have any questions.